Hello, am I audible? Okay, good. So today maybe we should wait for some 5 minutes. Can both of you check if you can access the link that I have posted, the questions? Okay, good. So we'll be having some MCQ questions only today, and next week maybe we will try to see a demo about inferencing of this deep neural network on a edge device, which is the NVIDIA Jetson Nano. We'll start it at about 6:05 today's session. I'm able to see only 10 questions in week 8 assignment. I'm not sure what you mean. This is not the link that you are seeing. It has about 32 questions. Oh, in the course there will be only 10. Yes. These are like in the live sessions we have like extra similar questions just for practice. I guess we'll start with the questions today. In the between, if you have any doubts, you can ask. So you can put your answers to the questions in the chat window, and if there is any discrepancy or if you have any doubts, you can let me know. We'll switch to the tablet screen. We'll discuss the answers and maybe then we'll switch back. Okay, I guess we have answers for some of the questions. Uh, so the first question's answer is not Adam optimization. It's actually LAM. So LAM essentially it stands for layer-wise adaptive moments for batch training. So this optimization algorithm is specifically for these large-scale neural networks and not for our usual neural network training. So in most usual training, you might be using Adam optimization, but in case of large neural networks, LAMB is a preferred option. It was discussed in the content of this week's course. So one is actually D. Hello? Yeah. So second one is also we have one answer. Which technique compresses a neural network by sharing parameters between similar layers? So it's essentially weight sharing. Pruning, quantization, or distillation, these we'll come to them later. So instead of similar layers in the sense, let's say convolution and followed by its activation. Okay, the answer for the first one is just LAMP. It's a different type of activation optimization algorithms rather than the Adam optimizer which we are commonly used. LAMP is more specific for large scale neural networks, and in case the batch size is huge, you want to optimize it using a different optimizer, and in those cases LAMP is a preferred choice rather than Adam. And we are discussing the answer for the second one right now. So second one is not knowledge distillation, it's actually a weight sharing. And the third question is how does knowledge distillation work? Okay, maybe at the end of these 5 questions we will discuss the theory of knowledge distillation. So the third question here is how does model accuracy change when converting from FP32 to int8 without calibration? So when we don't perform the calibration operation, we'll typically see a much reduced accuracy. It won't be as good as the FP32. Then which process in TensorRT maps activations to integer values? So that process is also called calibration. Okay, so that essentially is the calibration process. So mapping the activations to int8 precision rather than the model training might have happened in FP32 or FP16, or FP32 might have been quantized to FP16, but you might want to do inference at int8 precision. So in that scenario, the process for getting the same level of, or approximately same level of accuracy, is called calibration. Then we have which technique helps reduce overfitting by augmenting the input data during the training. So that is called the data augmentation process. So during training process, you might want to perform some data augmentation operations, and if you want, we can discuss some more details about it. But these are the answers. So the first answer is D, second is A, third is B, fourth is B, fifth is also B. Okay, so the one chat question we have is knowledge distillation. So maybe we can cover that. So I'll just briefly explain the idea of knowledge distillation. I hope my tablet screen is visible. Okay, good. So so this is actually a technique where you try to, so let's say you have a very big neural network or very big model. So this is model 1, which is, let's say, a very big model in terms of the number of weights. And overall the size of the network is very huge. So that is what a big neural network would mean. It may be a traditional neural network or some more different architecture, but in general it has a lot more number of weights or parameters. Okay. Now if we want to use or do some inferencing with this model on for some application, so the idea is that this huge model has a lot more number of parameters and weights, and we can't, let's say, put it on a small edge device, let's say a smaller processor like, let's say, Jetson Nano or some similar processors. So the big model we can't put on a smaller edge device. I mean, we can just store it, but we may not be, let's say, able to do inference from it. So let's say if you have a typical large language model, even in those cases the size of weight itself, in having some billions of parameters, in those cases the 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 memory that the ne- the weights of the network they themselves consume can be some orders of some 8 GB or something. And a typical small if you can a smaller edge device, it might not even have the GPU RAM itself. It might be, let's say, some up to at max 4 GBs or 2 GB. In such scenario, you can't put even the weights of this neural network onto the GPU of that device. So in such a scenario, you can't use this big trained model that you have, which is probably a very good model, but you can't use it directly for inference. Okay, so the idea in such a scenario is that you try to you use this model 1, which is a trained model. Let's call this as an optimized model. Okay, but you try to train a second model using this model, which is a much smaller model, and it has a fewer number of weights, fewer parameters. Okay, but now you might say, how can this model capture the same information that the bigger model was actually capturing? So in such a scenario, what we do is we want the original model which we trained might have been trained for a very huge data set, and the information that it is capturing in some form, it might have some redundancies, or the all these weights that it has, it need not necessarily have the most compact representation of the function approximation. Okay, so whatever are the various inputs that come to the model, it might not have a very compact representation to get it into the outputs. So we aim to get a more compact representation in this model 2 using the trained weights of model 1. So what we will do is, for this model 2, we will give the same inputs that we had for so we'll maybe take an example. So let's say you are looking at a problem of some classification. Okay, in such a scenario, what you would typically have is let's say this is the input layer, this is the output layer. Typically what you would have is this output layer. It might generate so whatever the output classes you have in the model, it will generate a probability for a particular input to belong to each of these classes. Okay, and you will basically, the model 1, what it must be doing is it basically chooses the output with the maximum probability and predicts that as the class. Okay, so what we do in this model 2 while training the model 2 is that we, instead of taking only the output that the model 1 was giving out, or what was the actual labeled output of the training process, instead of using just that, for the model 2 we will have all of these classes, and we'll train the weights of model 2 to match even the probabilities that this model 1 is generating. Okay, so I will maybe write it down. So model 2 will try to mimic even so this the typical when we usually do the training, you have a particular input and you have a particular class. So the class is, let's say, C, maybe C1, C2. These are all the classes, and the model ended up giving C3 as the output for a particular case, and the actual output is maybe C1, the true label. What we try to do is the output of the model typically comes out as C3 itself, like the only one of the quantities, because the model ended up predicting the highest probability for C3. So in such a scenario, if we try to do the updates based on only this one value of so C3 will be the one that is going to get affected throughout, and weights coming to C3 are the ones that are going to get tuned first. So this is called something called the hard update, because we are telling the model that this is the only answers, and you can't have any probability for any of the others. So it's a hard update. But in this training of this model 2, the smaller model, what we are doing is we are not saying that it should only predict C2 as the output. In fact, we are asking it to generate the same probabilities for each of the classes that our model 1 was generating. So let's say model 1, after its complete training, for a input of class C2, if the model was generating or giving out some probability of 0.9 and all the others some 0.2, 0.6, 0.2, something like this. So what is going to 0.0. So what is going to happen is we are going to ask the model 2 to mimic even these probabilities. When it tries to do that, it's going to have it's going to basically try to mimic this model 2 even in the representation of the different inputs. So how the different inputs are related to each other, that also it will end up learning. And since the size of this model is smaller, it has to forcefully learn all of that more in a more compact manner. The same amount of information you want it to learn, but you are forcing it to learn in a much smaller amount of weights. So that is how you basically do the knowledge distillation. So this model 2 is now a smaller model which has a more compact representation of the same kind of information that model 1 was having. And that is how you achieve knowledge distillation. Is that making sense? If you have any doubts, you can ask. Okay, I hope that answers the question. So we'll move back to the MCQs. wait. Shall we discuss the answers of this question? Or do you guys need more time? Yeah, 1 to 5 is done. Okay, so we'll discuss the answers. So sixth question, aimed at reducing the so that is the weight quantization, which is B. So 6 is B. Which of the following is an inference optimization techniques but not directly a compression method? So autokernel tuning would be the answer. So each of the others actually reduce the size of the model itself in some form. So even in case of pruning, you are specifically removing some linkages, so you can basically set those weights to 0. 6 is weight quantization. B. So 7th will be also B. it's not D. So pruning will actually you are basically removing some connections of the neural network. In that sense, if you are setting those weights to 0, you are saving the storage on those. I mean, they may not even be. You can even remove some neurons of the network and it will work out. I mean, if you have removed some, let's say, some layers of network, or some, in some sense, you are saving the compression. I mean, you're saving the memory of storing the weights for those, right? So in that sense, okay. So orthogonal tuning, that doesn't. It's an optimization on the processing side. It's not an optimization on changing anything with model. So 7 is B. Then 8 is what process removes entire. So 8 is actually A, pruning. So you will remove entire filter. So this is actually called more structured pruning. So you specifically look at some filters and you notice that they are not any. In pruning, entire filter is wrong. Yeah, I mean, there are two types of prunings. There is an unstructured filtering, unstructured pruning, and a structured pruning. Uh, in, in this case, we are looking at so if you remove a particular filter, let's say after training, you find that this particular filter doesn't lead to any capturing of any new features, or it is mostly inactive. Then you can specifically go ahead and remove that filter. Then your the network size is also reduced and you have optimized the network. So that is a more research oriented approach to. Okay, so in that sense, so to reduce the network size, we can go ahead and remove some filters by after researching how the filters are actually looking at, and in that sense, that is the answer. So A, pruning. Low rank factorization will be like representing a matrix operation with a in a bunch of with its a different type of matrix, which will, so in that sense it still has the same weights. You have not reduced the model size itself. It's more like a processing trick. Then which of the following techniques reduces model complexity without explicitly reducing number of parameters? So yeah, so in I mean in general, hyperparameter tuning is no, wait a minute. Yeah, batch normalization. So 9 no okay, there is a, yeah, 9 is C. It's more sensible to have it as C. So batch normalization, in that you are not specifically reducing any models. In fact you are adding some more parameters the when you are doing the normalization step. So it it makes the training process better in one sense, but uh, it's in fact adding more parameters. It's not reducing any parameters. So in hyperparameter tuning, in the sense you specifically reduce the size of the network and change some things, and in that sense it's a hyperparameter tuning. You can reduce the complexity of the model, as well as while you do that you can remove some parameters. Pruning is really removing some parameters. Certain weights of the network you can literally remove. Knowledge distillation is also changing it with some new model, which is of a smaller size. So as we discussed in the first set, so knowledge distillation also reduces the parameters. But in case of batch normalization, you are not reducing anything. The model complexity is not reduced. so 9 is C. And then which format does TensorRT use? So 10 is ONNX is a commonly used format. Yeah. The 10A is also there. Yeah. So 6 was 10 has multiple answers. Actually, yeah. The for in fact when uh, when representing a network from uh, let's say you borrow a network from TensorFlow or you borrow it from uh, let's say PyTorch, there might be different ways you can uh, have it represented. So it, this is ONNX is a more I think A would be the more relevant answer here. Okay. Okay, I'll just explain briefly the idea of batch normalization. So just to summarize the answers here, 6 is weight quantization B, 7 is B, 8 is also no, 8 is actually A, 9 is C, and 10 is A. Okay. So we'll just switch to the screen for some time and discuss about batch normalization and why I said it actually adds more parameters in some sense. So the idea of batch normalization is that let's say you typically see these problems of vanishing and exploding gradients in networks such as RNNs and LSTMs. So in those cases, you have in the gradient update step you have something like del ht by del ht minus 1 and some del ht minus 1 by del w, some weights. It could be any weight with respect to which you are taking the update. So del L by del is proportional to this. Okay. So what might end up happening in this scenario is that if when you keep having it, so in these LSTM and RNN networks, you basically have inputs coming it at different times. Okay, but the weights at each so the weight that we are actually trying to learn here, I'm just writing it here, it's W, and I will say x1, x2. So a typical RNN operation would, after unrolling it, it might look something like this. So you send in some input x1 at the first time step. The RNN neuron, it basically processes it. When it goes here, it's actually update this W1. This W weight is actually acting on it. I should call it WX so that you can separate it from the hidden layer weight. hidden state weight. So the idea is that uh, when you take, let's say this is your output at final time step, you are taking some output. When you compute the loss of some actual value y against this y6, so your loss is actually w minus w6. What you end up happening is that you try to take del L by del W, let's say X. You want to update this WX. This WX is shared throughout the time. So when you try to update it, you end up, when you take the derivative at this time step, also it is WX is coming. But this quantity is actually a function of what came out from here and this output, which was also multiplied by WX, and this quantity itself came out from this neuron and it's also a function of WX, and this quantity is also a function of WX. This also, so it kept on happening, and you have this multiple dependency on WX at each time step. So when you take the gradient along so many times, what happens is, if this quantity at any time, if it was less than 1, you are multiplying by something less than 1 again and again, and you end up going to 0. And instead, if you have this quantity greater than 1, you are multiplying something again and again. The deeper the RNN, the more this problem will be prominent. If you keep on multiplying it again and again with a quantity that is greater than 1, it will explode. The gradient step will explode. So in case of vanishing gradients, this case where the value is smaller, something that can help is called the batch normalization. Okay, so the idea is that in batch normalization, whatever input data you are feeding at a particular batch, input, let's say, what you end up doing is, I'll just make it as an example of neurons. So your input is, let's say, a vector. It came in all of these. What you end up doing is, for each of the points in the data set, you have the same number of inputs. Let's say a 5-dimensional vector is coming in. Okay, for each of the training inputs. So this is input 1, data point 1. So this is input data point 2, and some similar input data point 3 is also going to come in this same batch. What you do is, you take the for each of these, you are going to normalize it using the mean and variance of this quantity, and essentially each of the data points you are going to normalize them, and they are going to come in a similar range, and that is going to allow you to have a more stable updates in the process. So that is the key idea of batch normalization. So the process that happens, so whatever comes in, and after applying the activations and all, you will again, in fact, you can put a batch normalization layer, and this same process will be repeated. And so in that case, again, none of the outputs are very big than any of the others for any particular input data point. Then the updates are more stable, and it will not lead to any these problems such as vanishing gradient. Okay. Typically, then you have to actually get the mean and variance. During training time, you can calculate those for the data points, but during inference, what you try to do is, you basically, over the training data set, you have you keep on computing a mean and variance at each of these stages where batch norm was used, and you basically store that, so that during an inference time you can use the same means and variance for the input that comes through also. So you are learning more parameters wherever the batch norm is used in between. So I'm imagining a more application of batch norm in the process. So if in cases where vanishing gradient typically is happening, you might see that your network is not learning anything. So you can kind of help it by introducing these batch norm layers and keep the gradients alive so that the weights keep on updating of the network. Okay, I hope that answers your question. Okay, in case you have any question, we will. Okay, so yeah, we'll move on to the next set. Okay, I guess we'll start discussing the solutions. So the first question is, so which features allows layers to be fused together? So the idea is answer for this is A, the kernel fusion. So previously some question was there about layer fusion. So this is essentially what layer fusion is also. After the discussion of these, we will just briefly highlight what exactly is happening during kernel fusion and how that helps in optimization or faster execution. Then we have what advantage does FP16 inference have? Yeah, so lower memory usage and faster inference time. So 12 is C, and inference with deep learning shows gradient stability by preventing large updates. So the idea is that in this case actually gradient clipping is the technique that is helping us. Okay, so the idea is that in case of these exploding and vanishing gradient problems, batch norm also helps, but you can prevent larger updates by using gradient clipping. So if the gradients are beyond a certain value, you basically clip them to a maximum value, and you don't take any step. You don't allow the model to update any further than that. Okay, so that is 13 is A. Then 14 is actually Onyx is also there. Torch script is probably not the one. I'll maybe check. So A and C both in your opinion? Okay, so we'll update the answers also. In fact, I was only considering C, but okay. So 14 is both A and C. We'll check that thing, and I'll update it. Then 15th we have which tensority feature selects an optimized inference kernel for a specific hardware target. So that is really the auto-tuning kernel. And 15 is then B, and 16th is what is the advantage of intent precision? So it is precision but faster inference. So B is again the answer. Okay. So we'll just quickly discuss what the kernel fusion operation is actually about. So in a sense, what kernel fusion is actually doing is using the fact that in your traditional architectures, there is going to be a specific way in which you are going to arrange the layers. So let's say you might have a convolution layer, and it will be followed by an activation layer. So maybe rel, and you have some convolution layer here. Okay. So what this convolution layer is essentially going to do is it's going to pass over a kernel on this entire let's say this is the output at a particular layer, and you are going to pass this kernel on top of this entire image. Okay, so this is going to slide over here, and that is going to generate you out new data, some values, and you then want to sum them up and put ReLU on top of it, right? So the idea is that when you so this value that comes just by summing it all, and then so summing the entries on each of the kernel. Okay, maybe I will draw it in a bigger let's say you had a 3x3 kernel. Can I change the color? Yeah. So let's say this red is your kernel which you applied on this green layer which is the output at a particular stage of the conversation. Whatever is the input in your green layer, let's say, and that is going to get multiplied with your kernel values. I hope that is visible. I can make it any bigger. But yeah, so the kernel K1, K2, K3, K4, K5. So all of these are the values on your kernel. Each of them are going to get multiplied with the underlying value of the image, and you are going to sum them up and put ReLU activation on top of it. So this process might be slower if you store the sum separately into your memory and then apply the activation function on top of it. Instead of that, if you while storing in your memory itself, you applied the activation function and then stored it. So the output here, which is going to come up. Hello, am I audible? I think I just lost connection. Okay. So instead of storing the sum and then applying the activation on top of it, what you do is you basically store the activation output itself and then store it in your memory. So this operation can happen in your kernel. So when we say kernel, it's actually basically a function which is going to run on separate threads parallelly. Okay, so this kernel function itself is going to have the sum, the product and sum together, that operation, as well as the activation application operation. They both are going to happen in the same thread, and you get the output saved as the output of the activation itself. So these two layers, you have kind of fused them together while processing, and you are storing the output. So you are saving the time of having to store and then call it again from your memory. So that is the main idea of fusing this layers, layer fusion or kernel fusion. Okay, I hope that answers the question. Okay, so we'll move on to the next set. Auto tuning kernel is something more like it's an operation. So there are various parameters that you can play around for a particular hardware to ensure that it will run the process faster. So we saw the idea of prefetching in one of the previous weeks. So idea there was that while the kernel is processing some output, you can get the data for that particular for the next operation, you can get it ready. So how long the waits should be so that the queues are handled properly. So this is a kind of optimization that is specific to that a particular hardware on which you are implementing, right? So those are the things that you basically auto tune. You don't, you can't fix a hard tune, like a specific way of doing it. You have to tune it based on the architecture or the hardware underneath. So that is where you use the auto tuning kernels. So some parameters which similar parameters which will go in the operation, you allow them to be auto tuned by the kernel function itself. That is called the auto tuning kernel. Okay. have almost answers to all of the questions. We'll start to discuss them one by one. So, which optimizer adapts learning rates based on the historical? So, the answer is Adam optimizer, and one of the popular ones. Which features of TensorRT is designed to optimize inference speed by fusing multiple operations? So, just as I was explaining for the layer fusion or kernel fusion, this is the layer fusion is the answer, D. So 18 is D, 17 is A, then 19 is quantization. We are essentially, quantization is related to storing FP32 weights in FP16 format. So that is you are basically storing it in lesser number of bits, the same activations, and the model size is also kind of reduced by, since it's the amount of memory it consumes is lesser. For 20th, which optimization technique is this? Sample data set scaling features. Floating point to integers, so that is the precision calibration or just the calibration. And then 21st is issue of vanishing gradient, as we just now discussed, batch normalization, and TensorRT helps. Yeah, so answer for 22nd is A, dynamic tensor memory. Okay, so I'll quickly recap maybe. So 17 is A, 18 is D, 19 is B, 20 is A, 21 is A, 22 is also A. Okay. So we'll move on to the next set. Okay. seem to have answers to all the questions. We'll just quickly discuss. So 23, knowledge distillation, as we discussed, is transferring knowledge from a larger model to a smaller model. C. 23 is C. 24, randomly dropping, that is dropout. So that is one of the regularization techniques, so which can prevent overfitting. 25th is both B and C actually. So TensorFlow actually has TensorFlow, TensorRT, there is a already for TensorFlow specifically they have a feature, but ONNX is also can be used. Then you first convert it to an ONNX and then you import it basically. 26th is hyperparameter tuning, yes. So 26 is D, 27 is B, low rank approximation, low rank factorizations, or 28 is primary use of dropout during training is to improve model generalization. So you are essentially avoiding overfitting. Hence, question 26. Reducing computation and speeding up inference time is not an optimization technique. So yeah, if you in knowledge distillation you are actually you can say in a sense that it's not optimization technique. It's not on the same model in that sense, you can say. So yeah, B and D can both come out. Okay, so now we'll move on to the next set. I think this is probably the last set. we have answers to all four of them. So technique uses precision of weights, but network's performance is close to original. That is weight quantization A, and smaller manipulations, that is mini batch training B. Correct. 31 is the dropout. It's one of the regression techniques. Then answer RT, yeah, that is also B, auto tuning kernel. So 29A, 30B, 31A, 32B. Yeah. So we are done with today's questions actually. In case you have any doubts, we can cover those, or we can close today's session. Okay, so if there are no questions, we'll close today's session. Is there a question? I see a raised hand. Okay. Okay, sure. We'll close today's questions. Today's session. Thank you for attending.